Hello. In a previous lecture, we have learned about curvature of a curve. So curvature of a curve, it is a non-negative number which measures the deviation of a curve from its tangent line. So in this lecture, we'll give the notion of sign curvature. So this sign curvature, it tells that so given a planar curve, when does that curve bend away from the normal or towards the normal? So before going to the sign curvature, so let me first define what you mean by orientation of curve. So let us take two curves. So let alpha and beta be two curves in Rn, and we'll also take this alpha and beta to be also, let us take it to be a smooth curve. Be two smooth curves in Rn. So we say alpha and beta lie in same oriented class if so there exists a bijective differentiable map phi from the interval I to j. So note that this I and j are open intervals. So there exists a differentiable map from I to j such that phi inverse is differentiable, and so the derivative of this phi is greater than 0 for all t belonging to this I. Okay. So alpha and beta lie in same oriented class if there exists a map phi from I to j such that phi and phi inverse both are differentiable, and d phi dt is greater than 0 for all t belongs to I. So if I take all curves in Rn defined on open intervals, and so this if I make a relation, so alpha is related to beta if there exists a bijective differentiable map phi from one interval to another interval such that d phi dt is greater than 0, then that relation, so this will be an equivalence relation. Okay, so so let us take alpha be a smooth curve. So this this square bracket alpha, so this is the oriented class of curves containing alpha. Okay, so now if I define, so let beta be defined on this open interval minus b to minus a to Rn be the curve beta t. So this is defined as alpha of minus t. Uh, yeah, so this t, it belongs to your uh, open interval minus b to minus a. So if I take this thing, so and then you take the equivalence class containing beta, so then this equivalence class containing beta is not equal to the equivalence class containing alpha. Okay, so here, so you check that, so this d phi dt, either it is greater than 0 or less than 0. So there can be only two equivalence classes only possible. So one for greater than 0 and another for less than 0. Okay. So here if I take, so this is my alpha, and uh, suppose alpha is parameterized on this interval AB, and you are giving this direction here. So this is my alpha A and alpha B. And what is my this beta? So beta, it is in the this opposite direction. So this is my beta. Okay. So beta, we sometimes call it to be minus alpha. So alpha, it has an orientation, and beta, it is in the opposite orientation of alpha. Okay, so this is about the orientation of curves, and now let me move to the definition of signed curvature of planar curves. Okay, so let us begin with a unit speed curve in R2. So let gamma be an unit speed curve in R2. Okay, so suppose this is my curve gamma, and this is my point gamma s. And now I take the tangent vector. So tangent vector at gamma s, so this is nothing but is your gamma dot s. So this is denoted by capital TS, so which is your gamma dot s. Okay. Okay. So now, so what you do, so you so rotate this tangent vector anti-clockwise by 90 degree. So you rotate this tangent vector capital T by 90 degree, So we'll get a vector which is perpendicular to this tangent t. So this we'll call it to be ns. Okay. So let ns be the vector at gamma s obtained by rotating ts anti-clockwise by the angle pi by 2. Okay. Okay. All right. So I have taken this gamma to be unit speed curve. So because gamma is unit speed curve, so norm of gamma dot s is equal to 1. So norm of ts is equal to norm of gamma dot s. So this is equal to 1. So therefore, so this implies that ts is an unit vector, and I am rotating this tangent vector by pi by 2. So again, the vector ns, it will be a unit vector. So norm of this ns, so this will be equal to 1. So ns is perpendicular to the tangent vector, and also it is an unit vector. So this ns is called the normal vector of gamma at gamma s. Okay, so this is a unit normal vector at gamma s. Okay. All right. So now, uh, so let us take this tangent vector gamma dot s. So we know that norm of this gamma dot s is equal to 1. Now if I take the dot product of gamma dot s with gamma dot s, so this will be equal to norm of gamma dot s square, so which is equal to your 1. And now if I take the derivative, so differentiate with respect to s, so what you'll get? So gamma double dot s dot product with gamma dot s is equal to 0. So this means that this gamma double dot s is orthogonal to gamma dot s. Okay. So we have this curve gamma, and so this is my tangent vector gamma dot s, and we have this normal vector ns. So this gamma double dot s, so this is again perpendicular to this gamma dot s. So this implies that, so this gamma dot s, it will be along this line. So it will be along this line. So therefore, so there exist, some number ks, which is a real number, such that this gamma double dot s, it will be equal to ks times the unit normal vector. Okay. All right. So this ks, so ks is called the signed curvature of gamma at gamma s. Okay. And now if I take norm in this equation, so take norm both sides in the equation star, so it will get norm of gamma double prime s is equal to mod of ks. Okay. So norm of gamma double dot s, so this gives you the curvature of this gamma at gamma s. So therefore, if I take the mode of the signed curvature, so we'll get the curvature of gamma at gamma s. Okay. So now we got the signed curvature of gamma at gamma s. So now let us try to find out what will be the explicit formula to find the signed curvature of a curve. Okay. So before that, let me make this remark. So suppose, so now you have a curve which may not be your unit speed. So remark. So if gamma t is a regular curve, not necessarily unit speed. Okay, so we define unit tangent vector the unit tangent vector t at the point gamma t, which is again it is a function of t. To be equal to gamma double dot t divided by norm of gamma dot t. Okay. And similarly, so we'll get this unit normal vector. So this is my say gamma t, this is my curve gamma, this is my unit tangent vector capital T, and then again you have this unit normal vector. So nt, uh, so this is the unit normal vector is obtained by rotating the tangent vector anticlockwise by an angle pi by 2. Okay. So now in order to get the sine curvature, so what you do? So you take the unit speed reparameterization of gamma, or you take the arc length reparameterization of gamma. Okay, so take the arc length reparameterization of gamma. Okay, all right, and so then obtain the sine curvature. Okay, sine curvature Ks. All right. So now, if I take the derivative of this tangent vector capital T with respect to t, so this is equal to derivative of this tangent vector t with respect to ts. So s is here the arc length parameter multiplied by ds dt. Okay, and this dt ds, it is again, so this is my gamma double dot s. So ds dt is norm of gamma dot t, and gamma double dot s is equal to ks from here. So it is ks times the normal vector, and then you have this gamma dot norm of gamma dot t. Yeah, so we have this thing here. Okay, okay, all right. So we have this relation here. Okay, so observe that, so 1 by norm of gamma dot t times d capital T dt is equal to your ks time this and s. Okay, so the left hand side, uh, it will be basically your, so this will be basically your gamma double dot s. Okay, all right. So now, so let us try to explicitly find out the sine curvature of a of given any regular curve. Okay, so let us take, so let gamma t equal to xt yt be a regular curve in R2. So regular curve means here, so if I take the gamma dot t, so norm of gamma dot t is not equal to 0 for all t. So this is the meaning of regular curve. Okay, all right. And in order to find the sine curvature, so what we should do, so we will take the unit speed reparameterization of gamma. We'll take the arc length reparameterization of this gamma. So take the arc length reparametrization of gamma. Okay, and uh, after taking the arc length reparametrization, again I will rename this as gamma for convenience. Okay, and then we should find gamma double dot s. So gamma double dot s, so it is equal to your d2 gamma ds2. Okay. So now, by the previous lecture, so this d2 gamma ds2, so this is nothing but equal to your gamma dot t times no vector product gamma double dot t vector product with gamma dot t divided by norm of gamma dot t to the power 4. Okay. So now we know this gamma t is equal to xt comma yt. So this gamma double dot s, so this will be equal to your, so you can find out this this cross product. So what we'll get here, so this will be equal to your the following thing. So this will be x dot x prime t while double prime t minus x double prime t y prime t divided by x prime t square plus y prime t square whole to the power 3 by 2 times this vector y prime t comma minus x prime t. So y prime t divided by root over x prime t square plus y prime t square minus x prime t divided by root over x prime t square plus y prime t square. Okay. So now, so if I take this vector, so y prime t minus x prime t. Okay, so let us take this vector. So this is uh, orthogonal to your x prime t y prime t. Because if I take the dot product of these two vectors, so this will be equal to your 0. Okay. All right. So, and the denominator here, so there the denominator is equal to norm of gamma dot t. Okay. So 1 by norm of gamma dot t times this vector is perpendicular to this vector. Okay. So here, so this one is nothing but the normal vector in t. And this we got the tangent vector. So here, so the normal vector is perpendicular to this tangent vector. So this we got. So therefore, from this equation, one, so from 1, so what we'll get? So gamma double dot S is equal to KT times the normal vector. So NT is the unit normal vector here. Okay. So therefore, so the sign curvature here, the sign curvature in terms of T, so it is given as follows: x prime t y double prime t minus x double prime t y prime t divided by uh, x prime t square plus y prime t square whole to the power 3 by 2. Yeah, yeah. So here note that, so this S, so S, how it is defined? It is defined, you can define it as follows. So ST is integral T naught to T norm of gamma dot T dt. And this S, so it is a increasing function. It is differentiable and S inverse also exists. So this T, again, it is also a function of S. So here this NT, uh, so it is a unit normal vector at T, and let me draw this diagram. So we have this gamma. So gamma T, we have started with the parameter T, and then we have taken the arc length parameterization. So suppose this is my point gamma T, and this again I can write T as a function of S. So this point will be something uh, gamma tilde of S, and we are taking this normal vector here. So this NT, so this is so NT here is your gamma dot T divided by norm of gamma dot T. Sorry, uh, NT is the unit normal vector. So NT is the unit normal vector, and unit normal vector of gamma, so which is equal to NS, which is the unit normal vector of gamma tilde. So what is gamma tilde? So gamma tilde is the arc length reparameterization of gamma. Okay, so because of that, so this kt, which is again you can write it as a function of S. So this kt, it becomes a sine curvature of this gamma at the point gamma t, or it is the curvature, sine curvature of gamma tilde at gamma tilde S. Okay. Uh, yeah, so we have given the notion of sine curvature. So now let me say, so what do you mean by osculating circle and radius of curvature? So let us take, so let Maybe I'll just give a heading. Radius of curvature and osculating circle. So let gamma be a unit speed curve with parameter s, and ks be the signed curvature of gamma at gamma s. Okay, so radius of curvature uh, it is denoted by r, so rs. So this is equal to 1 by mod of this ks when this ks is not equal to 0. Okay, and now let us take, so let cs, so this is a point in R2, so it is defined as follows: it is equal to gamma s plus 1 by ks times the normal vector. So you have this curve. So this is my point gamma s, this is the curve gamma, and this is my normal vector. Okay, and what is my this cs point? So you take the line passing through this normal vector at gamma s. So cs will be point somewhere here. And now what you do, so you take a circle with center cs and radius 1 by mod ks. So let alpha t be a curve in R2 satisfying the following. So this is my alpha. So norm of this alpha t minus cs is equal to 1 by mod of ks for all t. So this alpha is a circle with center cs and radius 1 by mod ks. So here I am taking this ks not equal to 0. So this alpha is called the osculating circle of gamma at gamma s. Okay, so this is the definition of osculating circle. Okay, so now let me tell you about the geometry of bending of this curve with respect to the sine curvature. Okay, so suppose I take this oriented curve in this way, and this is my orientation of this gamma. So gamma, it is a unit speed curve. Okay. And this is my tangent vector, unit tangent vector here. And this is my normal. Okay. So here, note that, so the curve is bending away from uh, this unit normal vector ns. So here, the sign curvature, so ks, it will be your negative. And now, suppose the curve is something like this. So this is my orientation of this unit speed curve gamma. This is my tangent vector, and this is my normal vector. So here the sign curvature, so curve is bending towards the normal. So the sign curvature here, so it will be your positive. Okay. And now suppose you have this curve, the orientation is given in this way. So this is my gamma. And at this point gamma s, so this is my tangent vector. Okay. And you are rotating anticlockwise by 90-degree angle. So we'll get this unit normal vector. So here, so you can see this curve again bending away from the normal. So therefore this curvature, so here it will be negative. Okay. And again, if I take this curve in the opposite orientation, gamma, so this is my tangent vector, and this is my normal vector. So here again the curvature is bending towards the normal. So the curvature here, it will be positive. Okay, so I'll stop here. We'll continue in the next class.